Black holes represent one of the most profound enigmas in modern astrophysics, embodying the extreme consequences of gravity as described by Einstein's general theory of relativity. These cosmic entities are regions where gravity is so intense that nothing, not even light, can escape once it crosses a boundary known as the event horizon. The concept challenges our intuitive understanding of space and time, yet observational evidence has transformed black holes from theoretical curiosities into confirmed components of the universe. To appreciate the potential threat they pose to Earth or our solar system, we must first explore their formation, types, and prevalence. The genesis of black holes typically begins with the death of massive stars. When a star at least 8 times the mass of our Sun exhausts its nuclear fuel, it can no longer counteract its own gravity. The core collapses, triggering a supernova explosion that expels the outer layers into space. What remains is a dense remnant. If the core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, it forms a stellar mass black hole. These are the most common variety, with masses ranging from roughly 3 to 50 solar masses, though some mergers detected by gravitational wave observatories like LIGO Virgo have produced black holes up to 150 solar masses. The event horizon of a typical stellar black hole spans about 10 to 100 kilometers in radius, comparable to the size of a small city on Earth. Despite their modest dimensions, their density is staggering. All that mass, compressed into such a tiny volume, warps space-time dramatically. Beyond stellar black holes, the universe harbors intermediate-mass black holes, which bridge the gap with masses between 100 and 100,000 solar masses. These are rarer and less understood, potentially forming from the direct collapse of dense star clusters or mergers in globular clusters. Evidence for them has emerged from observations of ultraluminous X-ray sources and gravitational waves, but they remain elusive. At the pinnacle of scale are supermassive black holes, lurking at the centers of most galaxies, including our Milky Way. These behemoths range from millions to billions of solar masses. Sagittarius A star, the supermassive black hole at our galaxy's core, weighs in at about 4 million solar masses, with an event horizon radius of roughly 12 million kilometers, about 17 times the diameter of the Sun, but still minuscule compared to galactic scales. Estimates suggest the Milky Way alone contains between 10 million and 1 billion stellar black holes, formed over billions of years from successive generations of massive stars. This figure arises from models of stellar evolution and supernova rates, corroborated by detections of binary systems where black holes accrete material from companion stars, emitting X-rays. Globally, the observable universe may host trillions of black holes, each a testament to the violent cycles of stellar birth and death. Notably, black holes are not static. They can grow through accretion of gas, dust, or even entire stars, and merge during galactic collisions, releasing gravitational waves that ripple across space-time. A key property influencing a black hole's behavior is its size, dictated by the Schwarzschild radius. Rs equals 2gm/c squared, where g is the gravitational constant, m the mass, and c the speed of light. For smaller black holes, this radius is tiny, leading to extreme tidal forces near the horizon. Larger ones, like supermassive black holes, have more gradual gravitational gradients. This distinction is crucial when considering threats. A rogue stellar black hole wandering close to Earth would exert devastating pulls, while a distant supermassive one might influence galactic dynamics without direct peril. Primordial black holes, hypothetical relics from the Big Bang, add another layer. If they exist with masses below a few solar masses, they could evaporate via Hawking radiation, a quantum effect where virtual particle pairs near the horizon result in net energy loss. However, for masses relevant to stellar or larger black holes, evaporation is negligible over cosmic timescales. This radiation, proposed by Stephen Hawking, implies black holes are not eternal. But for practical purposes, those we observe persist indefinitely. In our galaxy, black holes are not evenly distributed. Many reside in the dense stellar fields of the galactic bulge or halo. The closest confirmed black hole, Gaia BH1, lies about 1,560 light-years away in a binary system, its presence inferred from the orbital wobble of a visible companion star. While no immediate threats loom, the sheer number underscores the dynamic, hazard-filled nature of the cosmos. Understanding these entities' diversity reveals not just their destructive potential, but also their role in shaping galaxies, seeding star formation through feedback mechanisms, and regulating cosmic evolution. As we delve deeper, it becomes clear that black holes are not mere voids, but active participants in the universe's tapestry. Their existence prompts questions about gravity's limits and quantum mechanics' interplay with relativity. In the next sections, we'll examine how these properties translate into mechanisms of destruction and the realistic odds of such cataclysms befalling our world. The serene vastness of space, suddenly shattered by an invisible predator, a black hole drifting silently through the cosmos, its gravitational maw ready to ensnare anything in its path. This isn't the stuff of science fiction. It's the raw, unrelenting physics of the universe at work. As we venture into the heart of how black holes devour matter and entire worlds, picture Earth not as a safe haven, but as a fragile speck hurtling toward doom. The process begins, innocently enough, with a subtle tug, but escalates into a symphony of destruction that no planet can withstand. Let's unravel this cosmic horror story, step by terrifying step, where gravity becomes the ultimate villain. It all starts with the approach. Suppose a rogue stellar black hole, born from the fiery collapse of a massive star, wanders perilously close to our solar system, perhaps ejected from a distant galactic merger, or simply adrift after billions of years. At first, the signs are subtle. Astronomers might notice peculiar orbital wobbles in distant asteroids or comets veering off course. But as the black hole draws nearer, its gravitational influence intensifies, like a whisper, turning into a roar. Planets begin to feel the pull, their paths around the sun distorting ever so slightly. Jupiter, the gas giant guardian, might be the first to react, its massive frame acting as a shield, or a sacrificial lamb. The black hole's gravity warps the space around it, creating a funnel-like distortion where matter spirals inward, accelerating to near-light speeds. Enter the accretion disk, the black hole's deadly halo of doom. As gas, dust, and debris from disrupted comets or planetary fragments get caught in this gravitational trap, they form a swirling vortex of superheated plasma. Friction within the disk generates temperatures soaring into the millions of degrees, unleashing torrents of X-rays and gamma rays that bathe the surrounding space in lethal radiation. If Earth were nearby, this cosmic furnace would strip away our atmosphere first, boiling oceans and scorching the surface long before physical contact. Picture the sky ablaze with unnatural light, auroras gone mad as charged particles bombard our magnetic field, overwhelming it until raw radiation penetrates to the ground. Life as we know it, fragile, carbon-based, and utterly unprepared, would wither under this onslaught, turning verdant landscapes into barren wastelands. But the real terror unfolds closer in, where tidal forces take center stage. These aren't gentle ocean tides. They're the black hole's way of tearing reality apart. Gravity isn't uniform. It pulls harder on the side of an object facing the black hole than on the far side. For Earth, this differential would start as a stretch, elongating our planet like taffy pulled by invisible hands. Mountains would crumble, continents rift apart, and the core's molten iron would churn violently, fueling cataclysmic earthquakes that register off the scales. Volcanoes would erupt in global fury, spewing ash clouds that blot out the sun, while tsunamis, miles high, ravage coastlines. Humanity, clinging to survival, might huddle in bunkers, but the ground itself would betray them, fracturing under the strain. As the planet edges toward the event horizon, that infamous point of no return, the drama peaks in a process aptly named Spaghettification. Envision yourself falling feet first toward the abyss. Your toes accelerate faster than your head, stretching your body into a thin, elongated strand. Atoms rebel against their bonds. Bones snap, tissues unravel, and what was once a human form becomes a stream of particles, shredded by the escalating gravitational gradient. For a stellar black hole, this agony could begin hundreds of kilometers from the horizon, turning approach into prolonged torture. Supermassive black holes, with their gentler slopes, might delay the shredding until you're inside, but the end is the same: total disassembly. Planets fare no better. Earth would elongate into a noodle of rock and magma, its remnants feeding the accretion disk in a blaze of glory. Stars themselves aren't immune. If our sun encountered such a beast, it could be siphoned off, layer by layer, its plasma fueling quasar-like outbursts that outshine entire galaxies. The the solar system's delicate balance would shatter. Mercury and Venus plummeting first, Mars flung into eccentric orbits, perhaps colliding with Earth in a fiery embrace. Asteroids, those silent sentinels, would rain down like apocalyptic hail. Hundreds, over 100 kilometers wide, each impact dwarfing the dinosaur killer that struck 66 million years ago. Survival? A pipe dream. Even in a hypothetical binary system where a black hole orbits alongside a star, extreme tides would render planets uninhabitable, ejecting them into the void or dooming them to consumption. This gravitational havoc isn't mere speculation. It's grounded in observations of real events, like the tidal disruption of stars by supermassive black holes in distant galaxies, captured by telescopes as brilliant flares. Yet in our story, the black hole always wins, reducing matter to its singularity, a point of infinite density where physics breaks down. As we pull back from this edge-of-your-seat narrative, the question lingers. Could this fate befall us? In the final act, we'll confront the odds and humanity's slim chances against such cosmic predators. The cosmos as a vast, unforgiving arena where black holes prowl like shadowy beasts, their insatiable hunger lurking just beyond the stars' twinkling facade. The stars above may seem eternal, but beneath their glow lies a tapestry of peril, woven from rogue wanderers and accidental horrors. Yet, amid the dread, glimmers of hope emerge, human ingenuity clashing against the void's relentless pull. Buckle up as we dive into the razor-edge balance between annihilation and survival, where science meets speculation in a pulse-pounding dance with destiny. The threats aren't mere fairy tales whispered in the dark. They're rooted in the cold calculus of astrophysics. Rogue black holes, those nomadic predators ejected from stellar nurseries or galactic mergers, could theoretically barrel through our cosmic neighborhood. With the Milky Way teeming with millions of stellar black holes, the odds of a close encounter aren't zero, though mercifully slim, estimated at 1 in a quadrillion over Earth's lifetime. Imagine a stealthy intruder, invisible until its gravity betrays it, slingshotting past at thousands of kilometers per second. Our solar system, a delicate clockwork of orbits, would unravel like a frayed rope. Planets hurled into chaos, comets raining fire from the Oort cloud. The scene would erupt in a blaze of collisions, painting the sky with meteoric streaks as Earth's crust buckles under tidal fury. But here's the twist. Detection might save us. Telescopes, like the Vera C. Rubin Observatory, scan the heavens, hunting for gravitational microlensing events where a black hole's warp bends distant starlight, giving us years, perhaps decades, to prepare. Deeper dread stirs from humanity's own hubris, the specter of accidentally birthing a black hole in our labs. Particle accelerators like the Large Hadron Collider smash protons at near-light speeds, fueling wild fears of micro-black holes spawning from compressed energy. In this nightmare, a pinpoint singularity erupts, gobbling atoms one by one, growing exponentially as it devours the facility. Then the planet. The air thickens with panic, sirens blaring as the ground trembles, swallowing cities in an expanding abyss. Yet, reality bites back with reassurance. Physicists, armed with Hawking's radiation theorem, assert any such micro-black hole would fizzle out in femtoseconds, evaporating in a harmless quantum puff before tasting a single proton. CERN's exhaustive safety reviews echo this, deeming the risk negligible, lower than a cosmic ray strike birthing the same anomaly naturally. Still, the what-if lingers, a shadowy thrill reminding us that tampering with the universe's fabric invites unforeseen storms. Venturing beyond survival's fragile ledge, we peer into the uncharted realms past the event horizon, where physics dissolves into enigma. Cross that veil, and the world warps into a kaleidoscope of impossibilities. Time dilates to a crawl, light bends into loops, and matter compresses to infinities. Would we tumble into a wormhole's throat, emerging in a parallel universe where alternate Earths thrive? Or dissolve into a holographic echo on the horizon's surface, our essence encoded in quantum foam? Theories swirl like eddies in a storm. String theory hints at multiverses. Loop quantum gravity suggests a bounce rather than singularity. Black holes as portals? The idea ignites the imagination, evoking visions of starfaring explorers, harnessing them for interstellar leaps, bending space-time to outrun light itself. But the void guards its secrets jealously. No information escapes, leaving us to ponder from afar. Our probes and equations, mere whispers against its roar. In this grand cosmic theater, humanity's role evolves from victim to vanguard. Advanced simulations model black hole incursions, while space agencies plot deflection strategies, perhaps nudging threats with nuclear pulses or gravitational tugs from spacecraft swarms. Colonizing other worlds spreads our bets, turning Mars or Europa into lifeboats against stellar doom. And in the face of the unknown, curiosity fuels resilience. Observatories like the Event Horizon Telescope capture black hole silhouettes, demystifying the monsters and arming us with knowledge. Ultimately, these behemoths aren't just destroyers. They're architects of galaxies, forging elements in their fiery forges that birth life itself. Our story isn't one of inevitable demise, but of defiant wonder. A testament to staring into the abyss and emerging enlightened. As the curtain falls on this epic saga, the universe's dangers sharpen our appreciation for the fragile miracle of existence. Black holes may lurk, but so does our unyielding spirit to explore, adapt, and endure.